Hello my dear students, welcome to our Darasa Online. It's once again physics. My name is Mr. Samuel John. In our previous discussion, we talked about the transistor in the topic of electronics. So we had a topic. This is our electronics. And I told you before that we'll be having the second part of it. So it's now the subtopic of today is a transistor. As a switch. And if you remember, we mentioned that transistor can be applied in different parts of our life. One of the applications is you can use transistor as a switch, security systems and alarm system. So before we start this part of the transistor as a switch, let us remind ourselves of what we discussed in the previous part 1 of this topic. And as we start, let's have this as a start. The question says, in an NPN transistor, the input voltage is 5 volts. And the base resistance is R1. If the load resistance is R2, such that the base and the collector currents are 0.2 milliampere and 10 milliampere respectively, negating the base emitter voltage. So this is the information that we're given. We want to test whether you remember what we discussed in the previous subtopic on the transistor. The question says, part A, calculate the value of R1 and R2, given that the voltage across the collector emitter is 5 and the voltage across the collector supply is 10 volts. That's part 1 of the question. Part 2, and if we change the value of R1 and its values adjusted to 2.5, what will be the values of IC? Step number 1, you are supposed to draw the diagram representing the above the information. So let's start drawing the circuit diagram for this question. This is our NPN transistor. NPN. So this is the question says we had the load resistance, which is R2. That's where you have R2 here. R2 here. This is our supply voltage. And we're given this is R1 as the input. This is our input voltage. This is the base current, because this is the base, this is the collector, this is our emitter. And this is our collector current, of course. So we have the circuit as required. You're supposed to have the complete values. The values are provided information. From the information, we know that VCC, this value is equals to 10 volts, and the voltage across this. So here, that's why we have this voltage here is VCE. Equals to 5 volts, the voltage across that junction here. And this voltage here, we are told to negate. So it's supposed to be VBE. We are told this is approximately equal to 0. It's very small values, and we are told to negate that. So we are given the input voltage here as 5 volts. So the base current and the collector currents are given. So base current IB is given as 0.2 milliampere, which is 0.2 times 10 negative 3 ampere. And we have the collector current equals to 10 milliampere, which is equals to 10 times 10 negative 3. This gives us 1 times 10 negative 2 ampere. So part A of this question, we're looking for the values of R1 and R2. And you can see from this circuit, Where do we find R1? So R1 is found in the input circuit, and R2 is found in the output circuit. So you can suppose consider the circuit which involves the input and output. So if you remember, when you're applying the Kirchhoffs, if you apply the Kirchhoffs in this loop 1 and 2, for the input, from the input you have the voltage which is given as the input voltage. This input voltage equals to the voltage across R1, which is I1, base current times R1, plus the voltage across the junction, that's BE. So it's VBE. This is the input circuit, and give us the equation which governs the input circuit. If you know the input voltage and we have the base current, you can find R1. So here you are told that this VBE is 0. So from here you can see, since the base emitter voltage is 0, so we are left with VI equals to base current times R1. From where you can find R1 as VI over base current. So our input voltage is 5 divided by the base current is 0.2 times 10 negative 3 is the same as 5 over 2 times 10 negative 4. Combine there. So we have the input, that's R1, the resistance of the input across the input is given by, is 5 divided by 2, 2.5. This will be times 10 power 4, which gives us 2500. So we have 4 zeros, which means we can have 3. So this is the resistance of the input across the input circuit, which is given the name R1. Part B, okay, R2, you can find R2 from the output circuit. From this circuit, we have the VCC equals to the voltage across this R1. R2, I mean this is this is the collector current times R2, plus the voltage across this junction as VCE. Our VCC is 10. Our IC is given 1 times 10 negative 2. We have R2, which we are looking for, we don't have, plus our VCE is given as 5. So you have 10 minus 5, which gives us 5, which is 1 times 10 negative 2 R2. And from there, you can find the values of R2 as 5 divided by 1 times 10 negative 2, which gives us 500 ohms. So that's the values of R1 and R2 respectively, according to the equation. So this is what we discussed in the first part of this electronics, and we saw how to formulate these equations. From there you can find the current gain, voltage gain, and the power gain. Now let's see part B. Part B says, so if by changing the values of R1, its corresponding VCE changes and adjusted to 2.5, what will be the value of IC? It means here, the values of R2 is not changed. It remains as 500 ohms. The value of the R which is changed is R1. By changing that, and we are told VCE now changes to 2.5. In other words, the supply voltage remains the same as 10. And what will be now the collector current? So from here, you can see you are talking about the output circuit, where you have the supply voltage equals to IC R2 plus VCE, as we derived from here. So you have, this will be 10. IC is not given, but R2 is the same as 500 plus VCE is now adjusted to 2.5. 10 minus 2.5, I think you can know that is 7.5, which equals to 500 times the IC. Now, this gives us the collector current after changing the values of R1, which give us 70.5 of 500 using your calculator. So I have mine here. You can find the value of IC. 7.5 divided by 500 gives us 0.015 ampere. So that value equals to, it's almost 15 milliampere. So it's 15 times 10 negative 3 times 10 negative 3, that's millimeter. So that's how you can find the value of R2. That's what we did in the first part of this topic. Now, in our today's discussion, we're going to discuss about the subtopic known as transistor as a switch. But before we talk about the switch, you are supposed to discuss about the saturations and the cutoff state of a transistor. And after, we shall see now how do you use transistor in automatic switches and the RM system. So that's our today's presentation. So we want to discuss about the saturation and the cutoff state of a transistor. Finally, we shall see now where can we use this concept in application of a transistor in the automatic switches and the RM system. So that's our today's discussion. Now, to talk about the saturation and the cutoff state of a transistor, let's consider the previous circuit that we drew. This was our circuit. We had this NPN. You can use NPN or PNP. And this is our resistor, RL. This is our input. Of course, we have the voltage applied here, but you know the output is supposed to be collected across the collector and the emitter. So that's where you find the output. So this is our C, this is our base, this is our emitter. And let's consider that we are talking about the NPN transistor, such that here we have the base, so the collector current produced by base. And then we have the emitter current. Okay, you remember this is the common emitter arrangement. And at this voltage here, if you remember, this is the voltage across the VCE. Of course, it's going to be taken from here. That's where we have the output. This is the voltage across the junction, which is given them VBE. Now, if you remember, when we talk of a transistor, we have different types of transistor. We can have silicon and germanium transistor. Silicon, the base emitter, the voltage across the base emitter, that's which distinguishes the two types of transistor. For silicon, it may be 0.6 or 0.7 for silicon, but for germanium it's supposed to be 0.3, 0.4. So this is the type of transistor that you normally use. I said we can use NPN or PNP, or sometimes you normally use the transistor which are utilized by the materials made from silicon and germanium. We prefer silicon, if you remember in the class, and we know the reason why we normally use silicon transistor instead of germanium. So for silicon, first you know, for silicon, for this the base is 0.6, it varies 0.6, 0.7 volts. So that voltage across there. It varies from there. You will be given depending on the nature of the questions now. So, in other words, in order to produce the current here, if you remember, when you're talking about the diodes, because this is transistors made from these PN junctions. Now, if you remember for a diode, when you have a diode, if you remember when you talk of PN junctions, that was the type of junction we formed. You can have a forward or reverse. And we say that in order for the current to flow in the forward, you have to supply some of the voltage. Now that voltage should overcome, we have the voltage which has been created there, barrier, the voltage barrier, which now when you overcome that barrier, the current will flow. So even for a transistor, it means that for the input circuit, we have this I. The input voltage is given by IB, R input plus VBE. That is 1. And remember that current corrector is given by this times beta. Like that, in order for the base current to flow here, you must overcome this. Sometimes here, this VBE is 0.7. So the applied voltage should be greater than that voltage. Otherwise, we don't have the current. So the current will be established here from this question. You can see from 1. So the current, base current, will be given by VI minus VBE over R. That's the input resistance. So the one which determines the current flow is the difference between the input voltage and the VBE. So if the VBE is less than that, no way you can have the current. So in order for the base current to flow in the circuit, so the applied voltage, the input voltage should be greater than this value. This is the condition number 1. The input voltage should be greater than that. So now let's see here, when it happens, when V input is less than VBE, we talk about the very small. What happened? This is case number 1. What happened when the input voltage is very small, so that is less than that VBE? It means that we don't have the current here. The base current equals to 0. And then if this is 0, we know automatically from this formula, the collector current is also 0. If that is the case, if you remember from the output circuit, this was the input. So if you consider the output circuit, we have VCC equals to IC RL plus VCE. So let's see now the implication of that. The implication of this is that when the input is very low, so that it cannot produce any base current, automatically the collector current will be 0. The voltage here, the current across will be 0. And if this is 0, the whole of this will be 0. As a result, the VCE, which now we take as the output here, equals to maximum, equals to the supply voltage. That means the VCE, which you talk about the output, is approaching the supply voltage. We say this is the maximum voltage. What do you mean by here? So if we don't have base current, automatically we don't have the collector current. For this case now, the transistor is behaving as in the open state. It's open, switch as open. So it is in the mode of, remember we had 2 types. We have saturation and the cutoff. So this is the condition of a cutoff state. The cutoff means the transistor is behaving as an open switch, and such that most of the voltage will be dropping across the transistor. You can see, and this transistor will behave as it has very large resistance. Very large resistance means no current flows through it. So this is the case of the cutoff state. So remember, cutoff state of a transistor, the VCE equals the maximum power supply. That's one condition. Part B, let's go to second part of it. What happens now? The second case here, what happened when VI increases? Let's talk about increases. If it increases, It means that from this question here, the base current will be produced. So IB is produced. Hence, IC flows. And from the output circuit, we have VCC equals to IC RL plus VCE. So you can see now here, since this current flows, now the current starts increasing. It increases. When the current increases, it means that the voltage across this also increases. If this increases, so the voltage we could give it the output voltage equals to VCC minus ICRL. What happens? If this voltage increases, it means that the VCE reduces. It may be some of the current maybe flows, small current may be produced in the base. It produces the base current. That means it makes the transistor to behave. It means the current may be flowing through the transistor, but the VCE is moderate. It's moderate. So in that means now, that's the case where the input voltage increases. If it reaches a point where you increase these values more than that, further increase of that, what happens? When you increase this voltage, we all know from the principle of transistor. If you remember in your discussion, we talk about transistor can be used as amplifier. There's a regions where the transistor, it has the operating point. Not all the inputs will be producing the output. So we have the certain point where the transistor is operating as an amplifier. So we have the operating point of a transistor. So here we have the active regions where the transistor will be acting. So here from this concept, you can see that's where the area where the transistor will be flowing, the current flows. Now, where? We're supposed to find the point where it reaches now is not behaving as an active transistor. For example, when this increases, when the voltage increases, further increase of the input voltage. If the voltage increases, it reaches a point now, let's see case number 3. Further increases of the input voltage, it means now the base current also increases. And this makes the collector current also to increase. When this increases, it reaches a point now from the output, we have VCC equals to IC RL plus VCE. Let's find this now. What happened? VCE equals to the VCC minus ICRL. This is our output equation. And we said from the beginning, when the input starts increasing, so it produces the current, moderate current, which makes the transistor to behave. Now the current through the transistor will flow. So we have the output. This was given as the output will be produced here. So we have the small voltage range. We remember, when you're talking about a transistor, the output produced cannot be greater than the supply voltage. There's a limit where the output can be produced. So here, when the input voltage increases, it makes this current to increases. It increases, and it makes also these values to increase. When this value increases, it has a limit. It reaches a point where this now voltage is equal. We said the output will never be greater than that. So there's a point where this voltage will be equal to the supply voltage. So when that happens, it is when this current has been increased. So it reaches a point where these voltage are equal. The VCC and IC, the voltage across the collector resistor, so the load resistor will be approaching each other. As a result, the VCE is approaching 0. It's approaching 0. What do you mean by that? That is where you have the maximum current. This is the maximum current which has been produced. So this maximum current, IC, is maximum. And when we talk of maximum, it means even if we increase the input voltage, the current also increases. That values will never increase. It's like an example at home. When you have some sugar in a cup, when there's a point where increasing some sugar, we have the condition where those sugars which are to be added, they will never dissolve. So the current, when it is the maximum, we say it is said to be saturated. So there is saturation. Increasing the input will never increase the current. So this is the saturation of a transistor. So the transistor is said to be in a saturated state. At saturation state, the VCE is equal to 0, and this current equals to the maximum. Now, if you are told to find the maximum current, how do you find it? The maximum current is found from here, from this voltage. We say that this is 0 when VCC equals to the IC times the RL. So you can find the maximum current here from the supply voltage over RL. So this is the formula used to find the maximum current. So here you can see we have the condition where transistor can be acting as, can be found in a saturating state, or it can be found in the cutoff state. For this case now, VCE is 0, it means the transistor is behaving as if it has very low resistance. In the previous, when we have cutoff state, the VCE is maximum, which shows that the transistor is behaving as if it's like a very large resistance. For this case now, you can see we have 3 states of a transistor. We have the cutoff state, when the input is very low, and then we have somewhere the region where the transistor can be active, make some sort of amplification, and we have this linearity, linear. The current will be produced will be linear to that, and then we have the other state, the region where the transistor is supposed to be in a saturated state. So when you are given those kind of conditions, some of these conditions are used to make use of amplification, as others as a switch. Now let's see example number 3. We said this is a continuation of the first part of our topic. Example number 3. If you remember in the first part of this topic, we did 2 examples. Example number 3 is design a transistor circuit using a light-dependent resistor and other components to switch on a light when it gets dark. This is a competence question. So this is not a direct question. When you talk to design a transistor circuit, that means we make use of this transistor. When it gets dark, the lights will be switching on automatically. This is automatic switch, as I said. Okay, now to start solving this question, first you should know what do you mean by light-dependent resistor. It's LDR, light-dependent resistor. This is the type of resistor whose resistance depends the amount of light intensity falling on it. The light intensity falling of that on this resistor will make the resistance to change. If you remember the symbol for this resistor, if you remember you did in your class, that was the symbol for lighting. And then you see. That means the resistance will be changing depending the amount of light falling on it. And the resistance is inversely proportional to the intensity of light. If you remember, that's the principle that we did in the PN junction. We talked about the other components. It means that resistance depends on the light falling on it. Here, in the dark, when you have low intensity, resistance is very high automatically in terms of mega, 10 power 6, and so on. In the daylight, the intensity of light is very high. It has very low resistance. So knowing this now, and you're supposed to use this component to design a circuit, and then use other components. So I remember I told you before that we normally use the common emitter transistor. So step number 1, you should have, let this the R be the light-dependent resistor. And then you're supposed to have another, let's use as R1. And then R2, we have supposed to have a fixed resistor. And then you're supposed to have the lamp, and as supposed to be replacing the output resistor. And then you're supposed to have maybe, so you're supposed to have the common emitter transistor. And common emitter is a transistor. Just talk about a transistor in the NPN transistor. You can use NPN transistor or NPN. So I prefer using that. So step number 1, you draw the circuit. This is our circuit here. Okay, this is our normal arrange. This is our collector here, our base emitter, and this is the base current, and this is our collector current. So that's where you connect maybe the lamp. The lamp must be connected here. That means this is the output, so it can be switched on. So here, where do you connect those two components now? So we have a circuit should be drawn. Remember, for stabilized common emitter transistor, if you remember, we had a certain component here which should be incorporated here and the other. So that's where we have, this is the input resistance. So this is our input. Remember, this is our input voltage supposed to be applied here. Now, where do you connect this light dependent resistor? Let's try to check if it's supposed to be here, the base. So here, this is our light dependent resistor, LDR, and that's where you fix. We take this is our R1, this is our R2. So the supply voltage, some will be coming here, they can produce the base current. So the one which determines the base current is the voltage across here. So now let's see. This is what we call about the VBE of VCE here, and there's where we have the VBE. This is our supply voltage, which is given. Now, the circuit is drawn. Let's check whether this circuit drawn will make the light to be on when it gets dark or during the daytime. So to see how it works, you can see this arrangement. This forms the potential divider. So some of the voltage will be passing here from the supply voltage. Some of the voltage will be applied here. Let's talk about how do we find the voltage across R1 and R2 from here? And which one will be having the greater share of the voltage? For example, let's consider the circuit of this type. If you remember, if you had a circuit of, this is 24 volts, and it is now, this is R1, simple, and this is R1 here is 2, and this R2 here is 10 ohms. So we have this. To know the meaning of the potential divide. So some of the voltage will be produced here. How much has been produced here because of this? Let's take this V1 and this is V2. From the concept of potential divide, we know that V1 equals to the voltage across R1. This is R1 over the total resistance, which is R1 plus R2 times total voltage, which is 24, supply. So if you check, this is the 2 over 12 times 24. This is 4 volts. So the remaining voltage, which is given by this R2 over total, which is now R2 is 10 over 12 times 24. This gives 220. So you can see the values of resistance of the voltage. They have voltage depending the resistance. You can see this 20 voltage has been supplied because of the value of the resistance is high. So the share that we get depends the amount of resistance we have. A small share will produce a small resistance will produce a small share of the voltage. So the same principle applied here. Since the resistance, this is the light dependent resistor. When the darkness falls, as I said before, the resistance of this semiconductor material is tending to increase. When it increases, it means that most of the voltage from the supply will be found here. This voltage will be sufficient to produce the base current. And remember, we said a current will be produced where we have a sufficient voltage, which will be overcoming that voltage across the junction. So these ones, the voltage across here will be sufficient to produce the base current. As a result, the current across this now, this is our collector current will be flowing through the circuit, and as a result, the lamps will be on. In other words, if you want to make this switch, to switch on the lights during the daytime, you're supposed to interchange the values, this resistor. When this is at the top, it means when it gets now, we shall see now, during the daytime, it will be having a very low resistance, and most of the resistance will be found at the bottom. So that's how you can make use of a circuit transistor to design a switch. That switch will be, it's automatic switches. When the darkness falls, the light will be on automatic. I think I've enjoyed. This is where the application of a transistor can be used. And we know the principle that normally using the concept that the voltage that will be applied here will be sufficient to produce the current, and that current will make the output to flow, output current. As a result, any component will be placed here, can be operated. Let's example number 4. Example number 4 now. I think you're making a follow-up on this transistor as a switch. Let's example number 4 on this part of a transistor as a switch. We are given a circuit diagram. As you can see, is this the NPN transistor with the input voltage applied, the supply voltage given, and the collector current. This is in the common emitter, if you remember. Now, we are looking for, from this information that we're given from the circuit, the information says that in the above NPN transistor that we have seen, the input voltage can be varied from 0 to 5. The input changing from 0 to 5. That 5 is the supply voltage, such that the current gain is given. So the current gain here, the current gain of a transistor is given as 250. And the input resistance as 100k kilo ohms. This is 100 times 10 power 3 ohms. And then we are given our output resistance, or resistance is 1k ohms. It's 1 times 10 power 3 ohms. And the supply voltage is given as 5. That's the information. No. So the question is not ending there. That's the information you have. The question says, if the transistor is saturated, we know when transistor is saturated, we know that the VCE equals to 0. We are given from the information. The BBE equals to 0.7. We are required to find what? We are required to find the minimum base current for which the transistor will reach saturation. The minimum base current. So from here, we have all these informations are given. We have given this resistance, and this input resistance is given, and the input now is varying from 0 to 5. We are looking for these values when the transistor reaches saturation. Part A, find the base current when the transistor reaches the saturation. You are told to find the minimum base current. How do we find that? We know when the transistor is saturated, the first thing to find is the current, the collector current. From the information that we have, at the saturation, we said VC is 0. Then what? VCC equals to most of the voltage across the resistance will be equal to the supply voltage. So you can find this is the maximum collector current given by VCC over RL. Step number 1. If you want to find the base current, the minimum base current, you should know the value of the current at which the transistor starts saturation. So it starts when the VCC is given. So our VCC is 5. And our load resistance here, which is now 1, times 10 power 3, you get 5 times 10 negative 3, which is 5 milliampere. This is our collector current. But the question is asking, when this is the current at which the transistor starts saturation. So let's find the corresponding values of the base current. So how do you find it? Which is the question now. From the formula, we know that IC equals to, you talk of the current gain. So that's from this one. Current gain is given. So you can find the base current. The base current equals to a current gain. Base current equals to, yes, collector over beta. That's what you can find. You can make substitution. If you substitute the value of IC, which is given as 5 times 10 negative 3 over the current gain, which is 250. Using a calculator, you can find what is the current, the base current. This is the minimum base current at which the transistor will reach saturation. So let's find 5 e power negative 5, negative 3, divided by 250. You get 2. It is 2 times 10 negative 5 ampere. So the base current equals 2 times 10 negative 5 ampere. If you divide correctly, you get that value. So you have the corresponding value of the base current. So this is the minimum base current at which the transistor will start to saturate. Part B. Part B of this question is determine the input voltage when the transistor is switched on. And remember, when you talk of the transistor is switched on, it's supposed to be at this kind of saturation. That's where it's switched on. In the cutoff, the transistor is able to switch off. Remember, because the IC is 0. So we normally use cutoff state as transistor supposed to be switched on, off, and saturation. That's where the transistor now is on. So from there, you are supposed to find now from this information, we are looking for the corresponding this input voltage. So you know from the input voltage equals to base current times the RB plus VBE. We know our VBE for this silicon transistor is given 0.7 volts, and we know the base current now. We found that base current as 2 times 10 negative 5 ampere, and the values of RB. The value of RB was given as from the question. The RB was given as 100 times 10 power 3 ohms. So you are supposed to find VI. This equals to 2 times 10 power negative 5 times the RB is the same as 1 times 10 power 5 if you combine this power plus 0.7 volts. So here, these powers will cancel out. This positive and negative will cancel out. So you have the remaining is 2 plus 0.7. This is 2.7 volts. So this is what? This is the input voltage where the transistor is switched on. 2.7. So the values we are looking for, part A, you're looking for the base current for which the transistor will be saturated to reach saturation, and the part B, you're looking for the input voltage when the transistor is switched on. Now, sometimes from this information, as I said before, we have 3 states of a transistor. You're supposed to explain now from this part C, using the answers in A and B. Explain when will the transistor be switched on or off. So from here, you can see the values we got. The input voltage varies from 0 to 5 volts. This is where the maximum supply voltage is. We never reach, we never go beyond that. And we have seen that the minimum, when the VBE was 0.7, so from 0 to 0.7 volts. So this value we got here. This is the value, the minimum, the voltage at which the transistor now will start to be as saturation, to be switched on. So it means that from 0 to 0.7, remember, if the voltage is less than 0.7, that means that there's no way you can have the base current. So this is the condition when the transistor is set to be off. And when the voltage is from 0 here to 2.7, between that, 2.7, this is when the condition of the transistor is supposed to be in active state. And then when the voltage is from 2.7 now here to the maximum, that's where the transistor is supposed to be at saturation. So this is it, on, off. According to the question, the answer is the transistor is supposed to be on from 2.7 to 5 volts when the input voltage is from 2.7 to 5, and the transistor is supposed to be off from 0 to 2.7, but transistor is supposed to be in active region when it's from there. So remember, you can sketch, if you remember, you sketch this graph of the output and the this was the input against output. We found as this was the voltage was flowing like that. It reached a point where, so from here, somewhere here. So this is a region where the output voltage reaches the maximum. Remember, this is the equals to the what? Equals to the supply voltage. That means equals to the supply voltage. This is the condition when you have what? Cutoff state. And this region, when we can see this region where the current now see, we have the from above 0.7 or 0.6. This is the active region. But when it reaches when the current increases, when the input increases, reach a point where the output starts now decreasing to the 0. So this is the region where you have saturation. So you can see this voltage, the output voltage is approaching 0, but it will never be equal to 0. It's getting small values which is approaching to 0. So I think we have seen now how do we solve different questions involving saturation and the cutoff state. Now from there you can use a transistor as a switch. We have taken an example of one where you can use a transistor as a switch in the automatic light, but can be used in other, if you remember, we discussed about the multivibrators. So this can be applied in multivibrators, or when you have two transistors connected such that the output of one transistor is acting as the input of the other transistor. This is what we form a multivibrator. We form a switching system. So this is through the capacitor, through the resistor, and we remember we have different types of multivibrators. We did in your class. You remember this? We mentioned some areas where you can use that. When you have two transistors, whose saturation point differ, slightly difference, we can have one transistor connected in such that the output, so the output of one transistor will be feeding to the input on another transistor. This is what we form a multivibrator, and we mentioned types. We have mono, and we have bi, and we have stable multivibrators. So these are different types of the multivibrators, which shows how a transistor can be used as a switch in various ways. Now, okay, to finish up our discussion, let's see now the assignment that you have. We have the assignment that you are supposed to do to check whether you have understood this part of the lesson. So the question says, you are given a transistor which is in the NPN transistor. The way it's connected, it has the supply voltage of 8, and the voltage across the resistance is 0.8, and the amplification factor of a transistor is given. The input resistance is given. You are required to draw the circuit diagram to represent this information. Then you are required to determine the collector base current and the collector emitter voltage, and we talk of VCE. Finally, you're supposed to find the power and the voltage gain. Okay, this is the part of our last part of discussion. So I think you can do that. Step number 1, you are supposed to draw the circuit diagram, and maybe to show us the starting point, you draw the circuit in the common emitter. This was the common emitter arrangement. This was the supply voltage, which is given here. This terminal should be connected to the ground. We have, this is the input. Very simple. You have this is the NPN transistor. This is our collector. This is our base. This is our emitter. This is our base current. This is our collector current, IC, which flows there, and this is our emitter current. This is our VCC. So everything is there. That's step number 1. You should know how to draw this diagram, and from there you're supposed to find all the information required, because this input resistance is given and this resistance is given. I think I've enjoyed. So, okay, for this part of electronics, and you have seen that the electronics play part in your life. Stay tuned for more programs coming on this part of programs. Stay at home and be safe.